Hi guys, it's Mr. Young, and today we're going to talk about our 3 chi-square tests and which chi-square test we want to use for a given scenario. Recall that we've talked about 3 chi-square tests already, and that's all we're going to talk about. The chi-square goodness of fit test, the chi-square test for homogeneity of a population, and the chi-square test for association, sometimes called the chi-square test for independence. First, let's talk about the chi-square goodness of fit test. The chi-square goodness of fit test is the classic chi-square test. We use it when we want to talk about one categorical variable that we know the distribution of. The expected distribution of the variable is known in advance. This is something that we want to compare to. So think of our M&Ms. With our M&Ms, we can contact M&M Mars and find out the exact distribution of plain M&Ms, for instance. Once we know the color distribution of plain M&Ms, we can get our own bag of M&Ms, pop it open, tally them up, count our green, count our yellow, red, blue, orange, and brown, and determine, does it look like the amount of M&Ms of each color that we got is in the right proportions to suggest that our M&Ms follow the distribution that M&M Mars claims that they should follow? And that's the key question that the chi-square goodness of fit test hopes to answer. Is it likely that this variable, in this case the categorical variable M&M color, is it likely that that variable follows the distribution that M&M Mars claims? Key points to remember here: it's a single sample and a single categorical variable. The second test that we talked about in our chi-square unit is the chi-square test for homogeneity. You want to think of homogeneity as that word that you learned in science, homogeneous, a mixture that's all the same throughout. In a chi-square test for homogeneity, we've got 2 categorical variables. Very much the same scenario as a goodness of fit test, but now we've got 2 variables that we're looking at. And here, those distributions are not known in advance. We do not know what M&M plain or M&M peanut look like in terms of their colors. But what we do want to know about those colors is, do they appear to be the same? Do milk chocolate M&Ms and peanut M&Ms seem to follow the same mix, homogeneous, same mix? Do they have the same color distribution for these 2 types of M&Ms? And that's the question we want to answer. Is it likely that these 2 variables follow the same distribution? And just like the chi-square goodness of fit test is used for one variable from one sample, the chi-square test for homogeneity requires that you have 2 categorical variables that come from separate samples from 2 separate populations. Here are samples being the peanut M&Ms and the plain milk chocolate M&Ms. And the last chi-square test that we need to talk about is the chi-square test for association, remember, also known as the chi-square test for independence. Whether or not we call it association or we call it independence is not really as important. It usually comes from the problem. So while I'm talking, I'm going to correct those C's in association. Spelled right on the first few slides, not so much on this one. But the chi-square test for, let's just call it independence and ignore my terrible spelling. The chi-square test for independence deals with, again, 2 categorical variables. So it's very, very easy to get it mixed up with the chi-square test for homogeneity. But what you really want to try to keep straight about these 2 things, these 2 tests, the homogeneity and the independence test, is that in the independence test, your 2 variables are coming from one sample from one population. So our 2 bags of M&Ms that we would use for homogeneity, the plain and the peanut, don't quite work out for the independence test because it's not a single sample from just one population. So in this example, we need some new M&Ms. So let's just get a single bag of M&Ms. They'll be plain for now. And we're going to record 2 variables. We still need 2 categorical variables. So we're going to record their color because that's what we've been concerning ourselves with. And we're also going to record whether they're whole when we take them out of the packaging or whether they're cracked. This gives us a second variable to talk about. Are the M&Ms cracked or broken, or are they whole? Are they in one piece? You know, you always find those M&Ms that are split down the middle. So what we really want to ask ourselves, is there some association between these two variables? Is the color of an M&M associated or perhaps dependent on whether the M&M is going to crack or remain whole? So maybe the blue shell is just a little bit thicker than all of the other shells, which is going to give you a larger proportion of blue M&Ms that happen to be whole. So we're asking ourselves, can we somehow create a link between the color of an M&M and whether the M&M is whole or cracked? We want to know, are those things independent from each other or not? Because we're asking ourselves whether they're independent or not, we have to be sure, I keep stressing this because it's the most important part in keeping this test differentiated from homogeneity, they must come from a single sample, one population. So guys, hopefully that brief overview helped you keep straight the differences between our three chi-square tests. The goodness of fit for a single variable and testing whether or not it seems to follow a given distribution. The homogeneity test, where we test to see whether whether two variables seem to have a common distribution between them. And the association or independence test, where we check and see if two variables from one population seem to be interrelated in some way. Thanks for watching, guys, and if you're watching on Edpuzzle, be sure to answer the follow-up questions.